Okay, hi there. The last thing I want to do today is just talk a little bit about stacks and queues. So I'm going to use the slides from the textbook to sort of go through these concepts kind of quickly. The first thing is stacks. The idea of a stack is really very simple. The standard analogy is like a stack of plates. You put one on top and then you take them off the top as well. So it's a very simple sort of structure. And the way we're going to formalize this as a data structure is to have a stack where we can create the stack. Then we have a push and a pop method. So the push method will take a string and put it into the stack. And then the pop method takes one out. Is empty will tell us whether it's empty. All right. So here's sort of a warm-up client. What we'll do is we'll take in a test client here. We'll read in strings from the standard input. And so what this does, this main program here, it creates a stack of strings called stack. Then it repeatedly reads the standard input until there is no more input. And then what it's going to do is read a string from the standard input. If the string is a minus sign, then it pops and prints. Otherwise, it pushes onto the stack. So if we take this input 2b or not 2, when we pop, we'll get 2 out. So you can see that the first thing to be printed out here is 2. Then we push b, so if we pop again, we'll get b. Going back, we'll get not. So you can sort of walk through what, the state of the stack, what's in the stack, and then what comes out as you remove things. Stacks are really important in all sorts of things. They're used for throughout computer science in implementing various things. And one particular application that you guys have seen is in implementing function calls. So in my visualizations of function calls, you'll see that one function calls another, calls another, calls another. And there are red arrows sort of going back, dashed arrows, to tell you how to get back to where you started. So what we do is when we call a function, the active one is always the most recent one, and that's always the first one to be removed, is the most recent call. So it's the last one called is the first one to be removed. That's a stack protocol. And for stacks, we're pushing the new activation record to store the local variables. And then when the function returns, we pop that, we get rid of it. So you can see in the slide here, there's a greatest common denominator function written recursively, and it sort of does this kind of recursive call. And we use stacks actually to implement this kind of storage for these things. Here's a slightly geekier example. Well, I don't know, different example. This is a stack algorithm for evaluating infix expressions. So suppose I have fully parenthesized infix expressions. So like this, 1 plus 2 plus 3 times 4 times 5. How do you go about evaluating something like that? And it's actually, when you start thinking about it, it's not trivial. It's kind of a hard problem. And so this guy Dijkstra came up with a solution, which is to use two stacks. So when I see a value, I push onto the value stack. When I see an operator, I push on the operator stack. Left parentheses are ignored, and right parentheses cause computation to happen. All right, let's just watch this kind of thing in action. So here is Dijkstra's two-stack algorithm in practice. So here we have the example expression, 1 plus 2 plus 3 times 4 plus 5, written across the bottom. And what we're going to do is just sort of go through things one at a time. So first we see a parenthesis, we ignore it. Then we see a 1, we push it on the value stack. Then we see a plus, goes on the operator stack. Ignore, ignore, number, value stack. Operator, operator stack. Number, value stack. Now we see a closed parenthesis. At that point, we remove two things from the value stack and one operator. We perform the computation, and then we push the value back onto the value stack. Then we can see an operator is multiplication. Then ignore the open, 4 times 5. All right, and now we're just going to see closing parentheses. So the first closing parenthesis is going to be 5 times 4. That gives me a result. I push. Now the next one is going to see the multiplication, which gives me 100. And finally, I do the addition. So it works. It's kind of interesting, and it's actually pretty hard to do this. You know, you can think about it yourself. It's not immediately obvious how to do this. Why is this correct? Well, here's actually code to do it, by the way. So the code is not really very complicated. Here I have a stack of operators and a stack of doubles, and I continuously read data, and you can just see here if I see open or close or whatever, I do the appropriate thing. The tricky one is when you see a close parenthesis. So that's when we take the operator, and based on whether the operator is a plus or a times, we perform either addition or multiplication. So you can sort of see the code there. But why is this okay? Well, note that the algorithm, you know, whenever it's got something in between two parentheses, it's always going to be putting that result on the stack. So it's like we just computed there. You can see in red 2 plus 3. We're going to actually compute that and put 5 there. We just keep repeating this over and over again. And you can make this work in a more general way. But you know what's interesting about it is that this algorithm really computes as though the operator occurs after the two values. So it doesn't matter whether the operator is between or before. And once you see this, you can say, oh, well, if I always have operator before parentheses, I don't need the parentheses. This observation was made by Jan Lukasiewicz, and so and because he happened to be Polish, this is called reverse Polish notation. And it's something that's used a fair amount. So it's used in all sorts of interpreters, in particular PostScript, which is a drawing language for drawing pictures, and uses this kind of stuff where they used postfix commands. That was actually used by the authors of the textbook to draw the pictures in the prior edition of this textbook. Okay, so you know we've got something like this. That's the abstract structure we want. And how do you implement it? Well, there's a couple of obvious ways, right? One obvious way is to use an array. So I've got an array, stick stuff in it. I need to keep track of how many things I've got in the array, and then put things in the right place when I have additional space. We've actually gone through this example in an earlier class. I didn't really go through the code that much, but it's really pretty simple code. So what does it look like? Well, we're creating a fixed capacity stack. We have an array of that capacity, and we have a counter, which your book uses in for counters. They're counting the length of things. So is empty is trivial. It's just the stack is empty when n is 0. And to push something, what do? Well, you take the item, copy it into the array, and then you increment the counter. So what do you do when you pop? Well, you first decrement the counter, and then you return the value stored there. So this is a simple sort of version of this, the simplest thing you can do. And it does work. It's important that you get if you use post increment for push, you need to use pre-increment for pop, and vice versa. You can do it the other way around. But as we talked about in a prior class, in that case, you would start with n is -1 instead of n is 0. And you can sort of make it work that way. It's just fine. So some common things here that you need to think about, though, is that you might actually, what happens if you pop an empty stack or push into a stack that's too full? Well, then you're going to end up with some kind of exception, and you need to handle that somehow. And there are different ways of dealing with it. With popping from an empty stack, there's really nothing you can do. But if you're pushing into a full stack, of course, you might allocate new space. So we'll see that as a major subject here in a second. Another thing is, like, if with with pop here just returning and decrementing, it's actually going to retain a reference to the object that is in the array. So if this is an array of objects, the garbage collector can keep that object alive, even though morally it's not really needed anymore. So for that reason, we'll usually, after we pop, set the array element to null just to make sure it's freed up. This isn't necessary for most things, but for arrays, you end up with this kind of necessary, because when you keep the array alive, you're keeping everything in the array alive, even the things that aren't currently being used. So you need to make sure that you don't keep things that you don't need in arrays. You don't need to worry about this kind of null thing with anything but an array. So, all right. So to actually do this in a way where we don't have to worry about running out of space, it's pretty straightforward to do this with a linked list. So what do? Well, we have our first pointer, and we just keep track of all the things in the list. So when you push, you just put it at the front of the list, and when you pop, you just take it out of the front of the list. Simplest thing you could do. And the code is actually quite simple. So where our nodes are going to be these pairs, these item next pairs, we need to keep track of what was the first node. That'll be our first field. And to pop something, all we need to do is save the first.item, remember what it is, then delete it by advancing the first pointer, and then simply returning the item we saved. So super straightforward code. Push is also very simple. So with push, here it's written to save the old first pointer, create a new node, and set that new node to have the appropriate data. And in this case, we are initializing the not and old first into the item and next. So that'll push the string not into the stack. All right, so here's the completed code. It's, like I said, not really very difficult. And again, note here, we don't have to worry about loitering when we pop, because when we pop, the node that we pop is going to become garbage because no one actually knows about it anymore. So this concept of nullifying things or writing null, like we do here in pop, where s of in gets null, this is really only necessary for arrays. You don't need to do it anywhere else. All right, so that's great. And we can sort of see intuitively what's going on here. How much time and space do we need for these stacks? And when we talk about time, the time is how long do each of these operations take? And you can see that each operation is going to take sort of a fixed number of steps. And so what we say is that they are all constant time. The size of the stack is a little more complicated. So we're going to have a size of the initial stack, the object, the linked stack of strings object. Then we're going to have another bit of storage for each node. So we end up having some overhead, and there's a fair amount of that here because each object has 16 bytes of overhead, and then some extra stuff. And here, the actual bytes to store the pointers. So anyway, this is, more or less, you can get the idea. We'll use about 40 bytes for each item, and that's the amount of storage required. Okay, so that's a stack. What about a queue? Well, a queue is sort of also kind of, I think, a very intuitive concept. It's like a line you get into at a cinema. People go in the line and they come out in the same order that they went into. So if you're waiting turns at any anything in sort of where people are lined up, so it's a queue. All right, so the operations here are called NQ and DQ. We put something in, it goes at the back of the line. We take something out from the front. All right, and we can implement this with a linked list as well. So here it's slightly more complicated though, because if you think about it, we actually need 2 pointers. We need to keep track of the first thing, but we also must keep track of the last thing. So this is a difference with stacks. Stacks are a simpler structure because we only need 1 pointer to keep track of them. So what do we do with queues? Well, when we put things in, they go at the end using the last pointer. When we take them out, we remove them using the first. So first is DQ is going to be pretty much exactly like pop. It's just going to be the push operation, which is more unusual or different here. Okay, so what happens when we pop? Again, the code is the same. So what happens when we push or we put something into the queue? Well, we're going to do it via the last pointer, not the first pointer. There's maybe a little bit of special casing here we have to worry about, where what if the queue is initially empty? In that case, we need to update both first and last to put that object into the queue. So there's a little bit of special casing we need. And you can see that here in the actual completed code, where NQ has a special case for the empty queue in both NQ and DQ. Right? So if when you're actually getting it right, you're like, oh, that's true. When you remove the last element, you have to update both first and last. You can't just return it, right? Because last will then last needs to be nullified when you remove. Likewise, first needs to be updated if it was empty. All right, so that's queues. They're also interesting in their array form, and I invite you to think about that. So how would you implement a queue in an array in an efficient way? So it's a little tricky, because you find that what's happening in your arrays is you're storing things, sort of the back of the line and the front of the line keep moving forward in the array. It's important that you don't end up just copying the whole array back to keep it 0 indexed, because you'll end up spending a lot of time copying, which will make your operations expensive. So if you don't want to do all that copying, then what you have to do is what's called modular arithmetic. So as you move things around, you actually start, as you run off the end of the array, you come back to the beginning. You can see code that implements that in your Eclipse folder, and you can also see some discussion about that in the problem sets for the text. Okay, just very briefly, we've already talked about generics and iterators. Let me just mention them again here. This is a generic list implementation where I have the type variable here called item. And we think about implementing code here. It really shouldn't be that hard to do it with arrays. You can see with linked list, it is straightforward and it just works. With arrays, we'd like it to be straightforward as well. There's a little bit of a problem, which I already pointed out to you, which is that arrays don't play nicely with generics. So you end up having to write this in a terrible way, which is to say, I'll create an object array and then do this cast. And this causes you some problems as well. So you end up having to write in a something to ignore the warning, which is kind of sad. Anyway, the other thing to note is that with Java generics, you end up with some limitations, because generic types must always be object types. They're not allowed to be primitive types. So if you have a stack, it's not possible to have, say, a generic stack where you can put an int in addition to strings. You have to use objects, and ints are not objects. The difference here is whether or not you store the value of the int, the number, or whether you're storing the address of an object. So remember, we talked about this in a prior lecture, the difference between int and integer, and the similar sort of wrapper classes. So this is what Java does. It'll actually use these wrapper classes. And it's nice, as a programmer, you don't really have to worry about it too much unless you're worried about all the details of performance. But you can create a stack of integers and push an int, and that's just fine. What Java will do is it doesn't actually do what's on this slide. It does what's in my slides that I showed you. It uses the integer.valueOf method. And similarly, when you pop, it uses the int value method, so to get the values out. So, you know, it can get a little complicated, because if you try to compare things, for example, you can get in trouble. This code, for example, looks very innocuous and very nice. It does not, however, do what you want. And the reason is that the equality operator on the integer type is object identity. It's not value equality. And so the basic thing is we just avoid the wrapper types if we can. So we'd much rather use numbers than wrapper objects. Okay, so this is the result of this, but very sad. Okay, and generics are kind of complicated. There's whole books on it. And so here in this, we just limit things to be simple. Okay, so don't worry too much about it. The last thing I'll mention real quickly is something else we talked about, which is iterators. So it's an interesting problem to think about how do you go, let's suppose we want to go through the items that are in the stack without taking them out and without actually talking about how the stack is stored. So the Java solution is called the Iterable Interface. It's the basic idea that there's something I can just go through, some kind of list of things without actually worrying about the details of the storage, without changing anything as well. So Iterable is done through this protocol, if you like. We have an iterator method. The iterator method returns an object that allows us to go through the structure, whatever it is that we're trying to go through. How do we go through the structure? Well, we use these hasNext and next methods. So hasNext is a Boolean, which returns true if there is a next element, and then next advances us forward and returns one item. So this is a really nice thing, and what I showed you in a the class as well is that we can use this for each syntax, that's shown on the bottom left here, and instead of these sort of longer code on the right. It's a nice thing that was put in Java 5. So how do we implement an iterator through, say, a linked list? Well, our iterator here is a separate object. So here's the list iterator object, and when we want to get an iterator from the stack, it's going to create one of these objects for us. So initially it's going to have a pointer called current. Initially that'll point to the first element. And what we're going to do is say, well, that's kind of all the state we need. We need to know which item we're on. And when we hit null, that's when we know we don't have any more items. And how do we implement the next? Well, we just store the current item, we advanced current pointer, and then we return that item. Okay, so that's how you sort of return the next item. If you have an array, you can also do the same thing. So with an array, we have a index into the array. So, and for a stack, we want to start at the end of the array and then sort of go backwards down to 0. So we'll start it in and then go down until we hit 0. So you can sort of see the methods there. All right. Okay. So the book also, your book uses a bag data type as well. And what they use the bag for, a bag is like a bag of marbles. It's something that you can look at. You can look at your marbles, but you don't really care what order they're in. So unlike a stack or a queue, when I go through my marbles, I don't really know or care what order I'm getting them in. So your book uses this bag API to keep track of that. So it's like a stack or a queue without the remove operation. So you're just putting things in, and you don't really care where they went. You just put them in. Okay, so that's what I have to say about stacks and queues, and we'll see you guys in class on Tuesday, assuming it's not too cold. We'll see you then.